today we'll discuss the so-called saddle point approximation. Before, we addressed Laplace type integrals of real-valued functions. So this is the form of the integral. Now we'll discuss the same type of integral, but taking along some contour in a complex plane. And both functions f of z and g of z are analytical complex-valued functions. All right, so let's draw some arbitrary contour in a complex plane. Okay. Well, so we will be interested in the asymptotics of this integral for positive and large lambda. Okay, so first let's discuss the structure of this exponential function. So we decompose our function f of z into its real and imaginary part. So it's also suitable to introduce the parameterization of the contour. So gamma is parameterized by some single parameter s. So z is equal to z of s. And so the choice of s can be quite arbitrary, but it's very suitable to choose it in such a way that it represents the length of the curve of the contour measured from some reference point. I don't know. And we'll choose this reference point later. Okay, so since s is the length, then dz over ds modulus is equal to 1. Right. So since we take the integral along the contour, which is parameterized by this s, now our function f of z becomes the function of, effectively the function of the parameter s. So u of x of s, y of s plus I, v of x of s, and y of s. So effectively it's just u of s and v of s. Now we plug in this decomposition into our exponent. So what we have here is lambda to e to lambda u times e to I lambda v. So the most significant part of the integral is defined by the modulus of its integrand. So it's the modulus we are interested in. So this is our function. So let's take its modulus. And we clearly see that the modulus is entirely defined just by the real part of our exponent, the function u of s. Now, let's track the possible behavior of this u function when we move along the contour. Well, the behavior may be arbitrary, so it's a smooth function since it's analytical. So it may be monotonous or non-monotonous. Well, monotonous case is slightly less trivial, and we'll discuss it later. Right now, from pedagogical reasons, we'll consider the easiest possible case where u of s has a single extremum as we move along the contour. Well, let's suppose that its extremum is our maximum. So there is some point z naught corresponding to some parameter s naught, where this function u of s has a maximum. Right, and so it's up to us to choose the value of c naught, s naught, sorry, and let's choose it to be equal to 0. All right, so now let's plot the function the exponential function e to lambda u of s. Clearly, since lambda is large, this exponential in the real case, has a very sharp peak near the origin, and naturally only a narrow region near the origin in this parametric space contributes to the value of the integral. Okay, so it seems that the same kind of logic which worked for the real case integrals works here. Okay, let's follow it. So now our function f of z can be represented by its Taylor series expansion near the origin as a function of s. So here we go. F of z is equal to u of 0 plus, so the term with the first derivative is absent since it's the maximum, and there is a second derivative term taking at the origin. Now there is imaginary part, and the first derivative term coming from the variation, from the change of the imaginary part. Okay. So now what we need to do, we just need to plug in this expansion into our integral and take, so it's going to be a simple Gaussian integral, and take it. All right, so let's do it. So here we go. Here's the same expression. I rewrote it for you, and I introduced some shorthand notations for the second derivative of u function and the first derivative of v function. And we truncated this Taylor expansion at the first non-vanishing terms, right? So it's s squared quadratic term in u and linear term in s. So when we plug in into this expansion to the integral, well, what's going to happen is that we'll integrate along our contour in the vicinity of this critical point. Oh, not critical, sorry, the extremum point. So there is this slope of this contour near this point. So there is some angle alpha. So let's introduce the new variable z is equal to z naught, where z naught is this point, plus dz over ds times, taking and s is equal to 0, times s. Right, so it's the expansion of this curve representing the contour near this maximum point. All right, so what it does basically, it substitutes the full curve of the contour with a straight line. But since we are only interested in the narrow vicinity of this point, so it's enough because these tails, they won't contribute to the integral itself. All right, so here we go. So ds is equal to dz over ds. This is equal to 0 times s. As you remember, we introduced the parameterization in such a way that this derivative, the modulus of this derivative, is equal to 1, because s is the length of the curve. Right, so we represent this derivative in the exponential form, where alpha is the slope of this line, and this is 1. So here is our, ds, of course. So here is our change of the variables. So we plug it in here. Okay, and g of z, well, we'll consider it, so it is supposed to be a smooth function of z variable, so we'll approximate it with its value at maximum point z naught. All right, so now you clearly see that the exponent is a quadratic function of s. And well, it seems reasonable that we should complete it to full square and take the Gaussian integral. So what we do is, so by the way, this is simply f of z naught. So what we do is just we complete it to full square. So it's 1/2 u prime naught, and then okay, let's see, it's s plus v prime naught divided by u naught prime prime. Oh, it's I squared. Yeah, and plus 1/2 v naught prime squared divided by u naught prime prime. Okay, so and now it seems the integration is straightforward. So this is the full square. We introduce another change of variables, s plus I v naught prime over u naught prime prime is equal to t. And we end up with the Gaussian integral. So t changes from minus infinity to plus infinity. So this is going to be constant. So we factor out this exponential e to lambda f of z naught. And here we simply have e to lambda u prime prime naught divided by 2 t squared, and times this additional factor, which comes from the imaginary part of our initial function f of z. So it's e to lambda v naught prime squared divided by 2 u naught prime prime. Okay, and then we integrate along this. Okay, so dt is equal to ds, so it's a simple shift. So now we just, sorry about this, but so it's dt times e to I alpha. Okay, right, this slope. And the answer is trivial. So it's the square root. So it's the Gaussian integral. So it's square root of 2 pi divided by minus lambda u prime prime naught. Well, since it was a maximum, then u prime prime is always a negative. Okay. So hence the minus sign. Okay, and now there is a principal exponential contribution e to lambda f of z naught. And there is additional contribution which comes from the imaginary part, which is lambda v naught prime squared divided by 2 u naught prime prime. And of course, additional factor which comes from the fact that we integrated along the sloped line. So plus I lambda. So here I rewrote for you the result of our integration. And sorry, I forgot g of z naught term. All right, so there is something strange about this result. Well, first of all, well, this term comes in naturally, so it's the main contribution, the main exponential. But there is an additional term here, which is, well, it's proportional to this first derivative of the imaginary part of f of z function. It was absent in the real case. And so u naught prime prime, as you remember, is negative. So this is a huge diminishing contribution because it's a big negative exponent, which is kind of weird because we would expect that there appears only this dominating term. And one more strange thing is that in order to get this result, we actually shifted the variable of integration. So initially, we expanded our function in the vicinity of the origin of s parameter. But then t, so when But then we took the Gaussian integral, assuming that the integrand falls off pretty fast in the origin, near the origin of this t variable, right? That's what the reason why we made this approximation. So t was assumed to be small when we integrated, but if t is small, then s is large, right? So if t tends to 0, s becomes of the order of v naught prime over u naught prime prime. So it's no longer small, and that's a problem. So actually, this is a mistake in our computation. We can't do things like that. We never encountered this before because there was no negative, in the real case, because there was no complex component, imaginary component of this f of z function. But now things are different. So this result is obviously wrong, and we can't proceed this directly with this computation in the case of complex valued function f of z. So the technique should change. It should be somewhat more subtle. All right, so what shall we change? Well, the good thing is that there are points in the complex plane where the function f of z is such that both of its derivative, du over ds, as well as dv over ds, vanish. And those are the critical points of function f of z. So df over dz at some point could be equal to 0. But the problem, on the other hand, is that in most cases, these critical points don't belong to the contour itself. So it's somewhere, it may lie somewhere here. And the question is, what are we going to do about this? But fortunately, we deal with analytic functions. And that means that if we deform the contour smoothly in such a way that it doesn't cross the singularities of the integrand, then the value of the integral is unchanged. So what are we going to do? We keep the origin and the end of the contour fixed, but deform it in such a way that it passes through this critical point. And as you remember, all critical points of complex valued function, analytical complex valued functions, are the saddle points. So there are no maxima or minima, just saddles. And hence the name of the method, saddle point approximation. So we'll deform the contour so it passes through the saddle. And then the only restriction which we should impose, the only choice, which we should make, is the direction at which along which we pass through this saddle point. All right, so and now we are going to discuss these possible directions.